How are you all? Welcome to this third Fluent tutorial. So let's launch Workbench. Okay, then we're going to generate geometry, mesh, everything, and work in Fluent. So just to remind you, there are two ways to launch Fluent: through the Workbench or here using Fluent. So let's do it first with the Workbench. So that this will let you create mesh, geometry mesh and everything, or if you already have the mesh, as some other cases you can open directly Fluent with the other option. So we're going to work with this geometry. It's a very simple geometry. Okay, this is a pipe, so we have diameter, length, and the flow and the inlet. So we're going to work from laminar to turbulence, so we have correlations to know the values. So let's do first a 2D case. Okay, so to run fast and learn a little bit how to run to do the meshes. Okay, so we're going to go like this, and the length will be 7 meters, diameter 0.1 meters. Okay, so we're going to use symmetry in the 2D case. So let's work it out in Workbench. So here you have all the actions. So we need to access here in component different actions. So first we want to access geometry model. So just drag and drop. So select it here, put it here. Right click here, and you have two actions to create geometry: space clean and design modeler. So for this case, let's use design modeler, but probably space clean is more flexible. And I think the tutorials I gave you, they are done using space cleans. So design modeler is like a software design modeler now, but it's not very powerful. This okay, so sometimes it can be a little bit difficult to use. It's not very intuitive. So as usual, you have done some CAD. I won't go into details. You choose the plane. So let's say that we want to sketch in this plane. Okay, let me hide this. XY plane. Okay, so you right click here, look at. So now that we know we want to sketch there, let's draw there a new sketch. So you have the action here, new sketch. Select here the new sketch. Remember, right click, you have more options to rename, delete, whatever. So now that we select this one, we go into the sketching tab, and here you have all the options to draw your geometry. So this is a simple pipe, let's say a rectangle, so we put it there. So we are not very precise, that is in the origin, it's not a problem. So we draw that one, so don't measure anything. So now to give dimensions, you go here in this tab, you have different modify dimensions, and we start to give dimensions here. So the first one that I want to give is a vertical dimension. Select this one, click in this line, the other one, and then you select it here. So you have your dimension there, and you access here, and this one will be 0.5. Remember that we're going to use symmetry. Okay, so now the other one will be a vertical dimension. Okay, so we go here, horizontal dimension. So you select this, and then you go to the other extreme. Okay, so probably this is a little bit more tricky. And okay, select here, and then you have it there, H2, and let's put there 7 meters. Okay, then here you have the option to fit the screen. So see here that you have your dimensions, and at any point if you want to modify, now where is this, sometimes these lines are not located where you want the the sketches, the dimensions line, you go here, move, select it, and then you can move it and put it wherever you want. Okay, so select this one and then put it here. Okay, that is something that just visual. Now it's not like you're doing something wrong or right. So now that you have your dimensions, everything set up as you want, let's go back to modeling here. So we have our sketch. Okay, now we need to convert this sketch into a surface, and that surface we're going to generate our mesh. Okay, so as you go here, you have the action surfaces from sketches. So you have a sketch, this one selected, See here that base object, and then you have different actions here. So add material, and see that now we have a surface here. Okay, so we need to have the surface. So now select here. Again, you can change the name. You have several options there, but I will choose here just Fluent. This is not compulsive, but just to do it, we're going to move to Fluent. Just it's a good idea to have it. So remember, generate every option here. You need to always press generate as we did previously. And then we want to go to the dimension model. So here again you have it, mesh, drag and drop. So you drop it here in your geometry, and then right click here when you have the symbol, means that requires update. Right click. So you go here, update. So basically it's just transferring the geometry here into this format, and then you can use it. So let's wait a little bit while it does everything. Okay, so now we have geometry, and we can right click, edit, and then we can enter mesh model. Okay, so again here you have a few options just to the end, everything. So soon to selection, so see that we can fit it to screen. So here we have the meshing actions. So as you right click here, you have many actions. So see that we have a mesh that was generated, but we want to use a new method. So see here, when you click here, you can select your physics, your preference. So we don't want to use mechanical, we want to use CFD. So see that now this is updated, so we need to update it. Right click, update, and it will generate a new mesh for CFD, which still is not good. Okay, so we have this element, so we want to make something much finer. So look at that, right click, and now we need to start to insert methods. Okay, so for instance, let me add a sizing. See here that you have sizing. So sizing, you can add it to faces, to the whole face, or to edge, or to a volume. So let me select this edge, apply, and then you can add their element size. So let me say that I want to put it there 0.01, and see that here you have a visual reference. So as you go now, generate. Okay, will give you problems because that one you need to make it a hard. Okay, this one means you need to force that edge. Okay. Okay, see that you have your refinement there, and then it's growing with some default parameters. So let's do the same refinement in this phase. Okay. So insert sizing, select this one, put there 0.001. Okay, give you. Okay, so also a good idea, put it harder to force. So now the question is how we can control all this phase. So in 2D, we have the action insert here. You see, you will have the action phase meshing. Okay, so we can select the phase, apply. You choose the type of element. So we want to use quadrilaterals. It's a map mesh. Okay, and press generate. And there you go. See that now you have this space. So but still we need to control that. But just to point out what is the difference between a map mesh and a mesh, not map. So as you put it now, here is like the original one, the one that we were getting at the beginning. So you need to add many constraints to control this mesh. Instead, when you map it, it will be kind of a structured mesh. So it's a good idea always put it there. And it does a very good job, Ansys Measure, to do the mesh. So you have many options here, so there are options to control. So go to the help and it will let you know what it does. So the next thing that we need to do is to control these faces. So I can go again, insert Tizen, select the edge. Now we can select both edges, here and here, apply, and let's put here you have element size, but also you can put number of divisions. So let me put 100 and see there that you have the visual reference. Generate mesh, and see that still you have this stretching that we don't want. Remember, you need to add here behavior hard, just to force it to have it uniform. So now this is what we have. Okay, so probably it's a little bit difficult to see. So let me reduce, just for the matters of better visualization, this. So one of the things that I want to work into this, you see that it's very fast to do this one. So as you go to 3D, you will see things are a little bit more slower. So see that this is basically what we're doing. This is the spacing that we have, okay? So if you want to increase it, let's put, okay, let's put 140. Okay, and let's go back here to this and to this, okay? So now that we have this one, remember that also we can resolve the boundary layer, we can control the clustering. So as you go back here, okay, you have the options bias, so you can go here at bias, bias factor, you put a number there. So I will put here just a number, and see here it's showing you how it will be clustered, okay? So as you generate the mesh, see that now you have better clustering for the boundary layer. Remember that you will need to do this to the other side, okay? So see that here we didn't do it. So we go to this side, and again we add a bias. We put 10. Okay, see here that now it will add the bias here, so it's better to do it, choose the other direction. This is why I selected these two edges in different edge sizing. Okay, sometimes they will have how they're created, the direction vector is pointing in a different direction. So this is why I did this selection. So here, as I knew that I wasn't going to do that one, I just selected both there together. So generate, and see here that we have our nice mesh. And now the next step before moving to the Fluent is that we need to generate select the edges or surfaces where we're going to assign boundary conditions. Okay, so here you can select, see here that you can select volume, faces, an edge, or a point. So we're selecting edges here. So you click here, see that it's green. Right click now, and here you have create name selection. So I will call it inlet, then select this one, create, we'll call it symmetry, because there I will apply symmetry, or you can add there an axis where you put the body, you know, axis symmetric problem. You can select the top wall, I will call it wall, and then you select the other extreme. Okay, and click here, boom boom, dun, 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 dun. This will be outlets, bam bam bam, and you see inlet, outlet, wall, and symmetry. Okay, so you can explore all. So inlet that within us. So now that we have everything selected, by the way, when you add these patches, you need to redo the mesh. So you can do this before doing the mesh or after, there is no problem, but if you do it after, there is no need to do remeshing. So we have this nice mesh 2D. By the way, you select here in mesh, here in the bottom you see statistic. You can get some statistics in the number of elements that you have. So see that we have 7,000, okay? So this is a small mesh, but let's say we want to put more, okay? A better quality. So let's add here more elements here. So let me put here 400, 500, or let's say 700 better, okay? Generate, and see that finder mesh, okay? And here we have 35,000, okay? So it's the one you can go larger. So we're doing 2D, just try this. There is no problem getting large meshes, okay? It's relatively fast. So let's take this one for granted, but remember it's the one you can get something finer. So we close the measure. Remember to every now and then save everything. So I will save this one, we call it case test. Okay, so we have geometry mesh. You see that you have the check mark, everything is okay. So now we need to move to Fluent. So select Fluent, drag and drop here in the mesh, and now you see that everything is connected. So by the way, everything that we have done is parametric. So you can parameterize everything and do modifications automatically. And you see here when you have the lighting means that requires update. So if you right click here, update. The update here means that the mesh that was generated here is a very specific format for Ansys measure needs to be converted to Fluent. So there are many formats of CFX, whatever, HDF. So you can convert. In this case, we're transferring everything from here to here. So it will do the conversion. So here, then in the bottom, you have all the files. So one of the things that I don't recommend you to work using the Workbench because it will create a lot of files here. When you start to run Fluent, it will start to create backups and stuff like that. That can take a space, okay? A 2D file is not a big one, but sometimes 3D files can be really large and it will add a lot of stuff here. In any case, so now that we have checkmark here, this one means that you can enter, double click, so you right click, edit, or double click. So edit, now you enter here, and we're going to enter into Fluent. So something important, it will recognize automatically that it's 2D, okay? But here, remember to choose double precision, okay? Choose double precision if you have more than one processor. Just select here. So this is to run in parallel. So in my case, I would put 4, okay? And start. Okay, so we're inside Fluent. So here we read the mesh, and we are here. Here you have it. So your middle button, you can zoom in, zoom out. Left button, just pan. You cannot rotate because it's 2D, but you have here all the options. So what we need to set up now is the physics. Okay, so let's go here. So probably the tutorials I gave you, they do everything here in the ribbon. I prefer to work here. Now it's my vertical approach. Okay, so I'm used to this one. This is a new setup, that order that they have in Fluent. So let's work here. You go into general, you set up here some parts of the physics, the general. So we're going to use a solver pressure basis, and we're going to work with the steady simulation. Okay, so if you want to add gravity, you put it here. Also, you can do axisymmetric problems. So in this case, let's do 2D normal with symmetry here, but if you want, you can add this axis, then will be axisymmetric. In models, here you select all the models that we want to use. So remember, there are many of them. We're going to focus in turbulence modeling, that is viscous here. So if you double click here, you have many models available. We're going to work through this in the theory as well. So for the moment, let's use the default that Fluent is proposing, K omega SST, that probably is the most general one. See that you have many constants that can be changed. Okay, so let's say that one. Then go into materials, and let's change the working fluid. So by default, also Fluent use air, but you can use something different. So this is an incompressible case, so pretty much it doesn't make it's not important to have the right values for the properties of the fluid. So I will put here 1, then I will put here 0.0001. So this one will give me a Reynolds number of 100,000, okay, based on the diameter, and in the inlet I will choose a velocity of 1. Okay, we can do this because it is incompressible. Okay, so cell zone is you double click here, so clear here, and then here you have operating conditions. Okay, again reference pressure, and then also in your domain you can choose edit here the material name. So if you have another material like water, remember to choose it here. So by default we're using the only one we have, and then we go here boundary conditions, and here you can select boundary conditions. So remember in the meshing we gave this name. So inlet, you have many options here. Okay, so in this case I will select a velocity inlet, and I will give you value 1. And remember that we need to give also values for the turbulence quantities. So remember that previous lecture we will compute in this estimate. So here let's use intensity hydraulic diameter. Let's use a low intensity hydraulic diameter 0.1. Okay, if you want, you can know your correlations, and you can compare Fluent with your correlations as part of your homework. And then outlet design. We put here intensity hydraulic diameter 0.1. This one is 1. And this is a pressure outlet. Okay, it means that you let the flow go out. So you have many combinations. So sometimes people have the tendency to put a velocity in the inlet and also a velocity in the outlet. That say that is not correct because you are forcing the flow. So usually you give a velocity at the inlet or a mass flow at the inlet, and then pressure outlet, meaning that you let it go out, okay, in a natural way. Then you have the wall. It's a wall, nothing to do. So you click here, edit. You see that you will have different actions. Okay, so for instance, you have roughness. You can add roughness. In this case, it's a smooth wall, and then symmetry, which is asymmetry. Okay, but for instance, you want to use axis symmetric problem in general, you can set that you choose here axis. In this case, let's stick with symmetry, it's the same. Okay, so we have everything set, and this one is just interior, is the internal mesh. So we have our initial conditions, boundary conditions now we move here into method. So here we don't need to set up anything for the moment. And then method, this is your solution method. So Fluent by default is always proposing a couple method, okay, which is very fast, okay, very efficient, but the problem is that consumes a lot of memory. Okay, so if you have memory limitations, be careful. So as a rule of thumb, is you have a mesh that have 1 million cells, you will require 1 gig of memory. That is for a segregated solver. For a couple solvers, you will need to multiply that value for 3 or 4. Okay, so let's say that if you have 10 million cells, you will require about 40 gigs of memory. Since you use this kind of couple, the other option is the segregated solver. So all of the simple CPs are segregated. Okay, they use less memory. So let's use, in this case, simple is a good option. Okay, so here the memory requirements is almost proportional. So 1 million cells, 1 gig of memory. Use the default method proposed by Fluent. It is okay. Remember that momentum you need to have here. This is compulsory second order accuracy. You have many options, but for momentum you need minimum second order accuracy. Okay, so this is our setup. We go to controls. So this is a little bit more advanced features, so I won't touch this one for the moment. For this physics, it is okay. Then we go to initialization. So here we don't need to set up anything. Monitors also, later we're going toward that one. So initialization, we initialize the flow. So we have two types of initialization. So let's use standard. We give the value, and I want to initialize. Remember, these are initial conditions, everything inside your domain, from the value that I have in the inlet. So see that in the inlet I have a velocity of 1, this is 0, and here is the turbulent kinetic energy specific dissipation rate computed by Fluent, so you can compare with your correlations and see what you have. Okay, so as you press here initialize, now you are putting all these ingredients inside. So we have boundary conditions, initial conditions, we choose our numerics, and we're ready to run. But before running, let's set up a few monitors. So as you go here in monitors, so residuals, see that you have your residuals. So these are okay for our case. Okay, but then I want to add monitors of mass flow, let's say. So if you go here, report definition, right click, see new, and then flux report. And I want to have a mass flow rate. You give it a name, mass flow, and I want to compute the mass flow in the inlet, outlet. So remember, the method is conservative, so we should get something close to 0. And report plot, so it will plot here what you have. Okay, so I want to add another one, new, which will be in a surface, and it will be, let's say, phase average. Okay, I want the average value, and I want to compute, okay, the average value of y plus. So I give it a number, average. So while it's running, it will show me the average value, y plus. So that, okay, so here in theory it should be just wall where I'm computing that, report to plot, and okay, so you have your monitor here, so it's plotting. And remember, every now and then just save project. At this point we are ready to run. It's saving everything. You go here, run calculation, run, and choose 500 iterations, and then press calculate. Okay, so it's plotting your values. So let me stop here because I realized that I make a mistake here in this one. I'm plotting pressure. I should be plotting is turbulence, the y plus. So you make a mistake, and if you want to go back to fix that one, you go here, report plot. Select here, edit, and then choose the right variable. So instead of pressure, I should use turbulence, and then y plus. See that you can access all the variables that Fluent is computing, okay, and you can plot it whatever you want. So y plus, put it there, okay, and let's initialize again. I want to start from 0, but you can keep computing from that value. So, but I just want to start from 0. So if you want to keep computing from this value, just press calculate. If you want to start from 0, initialize and go ahead. So I initialize and I starting from scratch from 0 again. And here it is. So see my y plus, something about, I don't know, let's see where it goes. My mass flow, so see that at the beginning it's oscillating, but then it will kind of stabilize about 0. And here you have your convergence monitors. So let's see how long does it take, or if it converges at all. It should converge. So see that we have a large Reynolds number, 100,000. Then you can try to run at 10,000, 6,000, and you will see that it is much faster. And you can go laminar, a value is 4,000, something like that, and you will see that it will be really fast. So see, in this case, it's not converging. Okay, this doesn't mean that it's wrong, just meaning that, okay, it's a really high Reynolds number. Okay, so probably would be better to switch your iterative method going on steady, okay, or let it iterate a little bit more. But your indication, you shouldn't look at this one, you should look more at some integral quantity. So see that my mass flow is very stable, about 0. So this is a good indication. But I still see that are going down, down, down. So I hope they will go to 10 to the minus 3, minus 4, sorry, 3, 4. Okay, it's getting there. You see that arrive to the maximum number of iteration and I stop. Okay, if I want to keep computing, press again calculate, and it will restart from there. And you can do this one, you can change options here. So whatever you have here, you can change it and then calculate, and it will start from the solution that you have, and then it will use the new values. Okay, so it is iterating, hopefully will converge, and voila, we have a converge solution. Okay, it was a little bit slow, but our Reynolds was very high. And now we want to visualize the solution. Now here you have the results and graphics, contours. Save display, and here you have pressure, then you have velocity. So as you go here, see symmetry plane. As you go close to the wall, see that here you have your boundary layer. Okay. And what is interesting here, so remember a little bit fluid mechanics. I chose this distance 7 because here we have an entrance length. So the flow enters here, and you need to have a given length until the point that the flow is fully developed. Okay. So for instance, you put your mesh up to this point, you see that it's not fully developed. So then just find those correlations, and you will see that the dimensions I chose for this domain is kind of twice the maximum value, or the point where you have the fully developed flow. Okay, again, for instance, let me go and do some other plotting. So this is, you choose all your quantities here. Okay, whatever you want, you can choose it here. So you have access to everything here that Fluent is computed. So you can plot vectors here. So again, you go here and zoom in and see that here we have our velocity profile. And remember, this is a characteristic profile for turbulent flow, very uniform here. And then you have this strong gradients here. Okay, and then we can do some other plot actions. So there are many advanced actions. So but I want to use this one, XY plot. So this one I can use it to plot in a given surface. So I want to plot, for instance, in wall. And what I want to plot turbulence, and I want to plot the Y plus value. And the direction to plot is the X directions. That is okay. So see here, the beginning, large value, and then it changes. So you see, this is a very simple problem. As I told you, it's very difficult to have a uniform value. It's not impossible. See here that it's changing. Probably you let it very long pipe and will be in one point uniform, but it's not realistic. Something realistic. Actual geometries, industrial geometries, it changes a lot. Okay, but we look at the average value. So for instance, another interesting quantity you can plot like this, velocity, and I want to plot it at the outlet and also the inlet. Okay, I want to see the two profiles, and I want to see those here. Okay, I know that it goes in that direction. Save plot. Okay, so see that this is your profile at the outlet, and this is the profile at the end. So you chose uniform, and then here you have this one. Okay, and again, I don't want to plot the inlet. Okay, for instance, something interesting that you can access turbulence here, and you can plot turbulent kinetic energy. And this is that we know that the turbulent kinetic energy are the fluctuations. So we know that close to the wall in the viscous layer, we don't have fluctuations. So see here that it goes here to 0 close to the wall. Okay, and then there is one region where it's high. So usually it's very high in the buffer layer. So you have it laminar, and then the buffer layer is where you have the most energy. And again, you can show you can get also access to dissipation rate. So see here that dissipation in this case at the wall. Okay, and this is pretty much in balance. So if you check production and dissipation, you should get everything balanced. And for instance, turbulence viscosity, you can plot it and you see that in the core we have, okay, see here that you are having this value in the core. Okay, so this will have a direct influence on your Reynolds stress tensor. This is the value that we want to compute. And then close to the walls, it goes to 0. Where is the laminar? The viscous sublayer. Okay, so this is it. This is this easy case. Okay, so for instance, just to reduce something, so let me change air and let me change this value to this one now. So now the Reynolds should be 10,000. Okay, I want to initialize. I want to start from 0, but remember you can start from the previous solution, but I want to initialize just to show you that now the convergence rate, it is faster. So now go calculate, computing your quantities, mass flow, y plus. So see that you reduce your value, now your y plus is much lower. Again, also you can rerun this when different turbulence models, you will see different convergence rate, also different initial values, starting points, also different convergence rates. Okay, it's almost there. Hopefully before 500 we'll get there. Okay, we're there. So see that now 430, previously it was like 600, and we have the converged solution. So again, you can do your post-processing, plot there your velocity values, and now we can plot here also turbulence and this one. So see that here it's 0, close to the wall, everything is 0. Then you have a lot of fluctuation where you start to produce the fluctuations, all the turbulence, and then you go to the core. Okay, so you will see we see this in this case that we are resolving the boundary layer. When we are not resolving the boundary layer, now this will be a 0 gradient. It's not 0, the wall will take the first. So we're going to see that one when we work the tutorial, but also you can try to redo the mesh and you will see that behavior. You can plot also the dissipation. Okay, you have here, and then we have intensity again, where you have largest intensities, the largest fluctuations, and so on. And now let me go even the lower Reynolds. So let me put this one to 4. Okay, so now it should be 1000. So remember, it's not a good idea to use a turbulent model when you have a laminar flow. It doesn't mean that it won't converge, it will converge, but probably you will need to iterate longer. So this is another exercise. So try to run using the k omega in a laminar, and then you disable, you put it laminar. Laminar is disabled, means the DNS, and you will see that the laminar will converge faster. Okay, or probably you need to get the right profile with the laminar, you will need to iterate less. So you want to get the same profile using the turbulent model, you will need to iterate much more. So initialize and go. So here I left the model on. So let me stop it and let me switch it off. Okay, just to show you also some behavior. So you put it laminar, it's off. I want initialize, I want to iterate it from whatever I have, calculate. Okay, but I need to initialize. Okay, so no, sorry, it's not. It's telling me that, okay, it's related to y plus value. Okay, so yes, deactivate. So remember that you don't have Y plus, or you have it, but Fluent that doesn't compute it. Doesn't compute Y plus in Laminar, so it was telling you that that report function was invalid. So I just did deactivate it in the screen. Just when asked me, just deactivate, and see that now you only have continuity, velocity components, and that's all. Okay. And see, okay, so there is a smoother convergence. Hopefully it will get fast. And voila, we're here. Okay, so this is a laminar flow solution. You put here, okay, let me choose velocity. And you have your value. So see that now this profile is different from the previous one, the turbulent one, as you recall. See that this is a parabolic one. So at this point we can do all the sampling. We're going to work on that one, how to save these files, and then you can open it in MATLAB, whatever. So this was this case. So hope you follow the instruction. I will unload some other case 3D. Okay, but that's all. Thank you very much. Bye.